Hi everyone and Assalamualaikum warahmatullahi ta'ala wabarakatuh. I'm Madam Nurmadia, going to explain quantization of light in chapter 8. This chapter has two subtopics, which is a Planck's quantum theory and the photoelectric effect. Learning outcomes. At the end of this class, student can state Planck's quantum theory. Student can distinguish between Planck's quantum theory and classical theory. And student can use Einstein equation for a photon energy. E equals to hf equals to ht over lambda. Before we go into more detail about Planck's quantum theory, let me know what is a black body. So what is a black body? Black body we can define as the object or the system that absorb all the light that incident on it, no matter the wavelength of light or its angle of incident. A black body will absorb all the rays. Another properties of the black body is it also emits radiation, where that emission depends only on the temperature of the black body. Or we can say that the emission occurs at a different temperature. The distribution of this emission of the black body we known as black body curve. Okay, class, did you notice at this graph, different curve occur at a different temperature. Classical theory state that the distribution of energy in black body depends only on temperature T. According to this equation, E equals to kBT, where E represent for energy, kB represent for Boltzmann constant, and T represent for temperature where we measure in Kelvin. Besides that, classical theory also state that the energy of the electromagnetic radiation is emitted continuously and can take any value. Class, let me look at this graph intensity against wavelength. At this graph, we have two types of graph. The dashed line graph represent for classical physics by Rayleigh chain theory and Wien's theory, and the solid line graph represent for modern physics. Classical physics state that or predict that as the wavelength approach to zero, the amount of energy radiated should become infinite. But for the quantum physics or experimental value, state that as the wavelength approach to zero, the amount of energy radiated approach to zero. Because of that, the classical physics can't explain the observation distribution of electromagnetic radiation. That's why physics quantum are born. In 1900, a scientist, Max Planck, proposed a theory known as Planck's quantum theory. The assumptions made by Planck in this theory are: the electromagnetic radiation emitted by the black body is indiscrete or separate packets of energy. This packet we call or known as quantum of energy means the radiation is quantized. The energy of the radiation only depends on its frequency. According to this assumption, the quantum of energy is given by E equals to hf, where h is Planck constant 6.63 exponent negative 34 joule second, and f stand for frequency. Since the speed of electromagnetic radiation travel in the vacuum, which is equal with c lambda f, we can rewrite the equation concentrated, or a photon, also known as a unit of energy, equals to hf, which is E equals to hf, and travel at the speed of light in a vacuum. So they are required to explain the photoelectric effect and another phenomena that require light to have particle property. We can write as E equals to hc over lambda. Okay, this energy we know as the energy for photon. Okay guys, this is time to answer a question. We have one question. Okay, a photon of green light has a wavelength of 740 nanometer. Calculate A, the photon's frequency, B, the photon's energy in joule and electron volt. Given the speed of light in the vacuum, 3 exponent 8 meter per second, and Planck's constant, 6.63 exponent negative 34 joule second. So how we want to solve this problem? First of all, you need to list out or list down the information. We have a wavelength which is a 740 nanometer. For question A, the frequency of the photon is given by C equals to lambda f. C stand for speed of light, lambda is a wavelength, and f is a frequency. You just substitute the value of speed of light and wavelength, then rearrange this equation to get the frequency. The answer is 4.05 exponent 14 Hz. For question B, calculate the photon's energy in joule and electron volt. We want to find the photon's energy. So we use the formula E equals to hf. E stands for energy, h is a Planck constant, and f is frequency. Then you substitute the value of Planck constant, h, and frequency that we have calculated A, and you will get 2.69 exponent negative 19 joule. If you want to get in electron volt unit, so you just divide by 1.6 exponent negative 19, and we get 1.66 electron volt. So class, remember, when we use the formula that consists of Planck constant, our unit is in joule. Now we proceed to 8.2 photoelectric effect. I just discussed two learning outcomes from this subtopic. First learning outcome is define photoelectric effect, and the second one is explain the phenomenon of photoelectric by sketching diagram of the photoelectric effect experimental setup. Now consider we have a metal which consists of free electron, then electromagnetic radiation with a suitable frequency strike on this surface, and what will be happen? The electron will be ejected. This ejected electron we known as photoelectron. So this process or this phenomenon we known as photoelectric effect, and we can define as the emission of electron from the surface of a metal when the electromagnetic radiation of higher frequency strikes its surface. And photoelectron we can define as the electron emitted from the surface of the metal when the electromagnetic radiation strikes its surface. And now we look at a schematic diagram for photoelectric experiment. This experimental arrangement consists of cathode, anode, voltmeter, galvanometer, power supply, and rheostat. Negative terminal of power supply we connect to cathode, and positive terminal of power supply we connect to anode. When the electromagnetic radiation with a suitable frequency strike on the surface of the metal, the electron will be ejected, and this electron or photoelectron will be attracted to anode. Then the galvanometer that acts as emitter will be deflect, show that the current flow in this circuit. This current we call as photoelectric current. When there is an increasing potential difference between cathode and anode, more photoelectron will be attracted to anode. Because of that, the photoelectron will be increased. As positive voltage becomes sufficiently large, the photoelectric current reach a maximum constant value we call as saturation current, or IM. So what is saturation current? Saturation current is defined as the maximum constant value of photocurrent when all the photoelectrons have reached the anode. What do you think if we decrease the potential difference between cathode and anode? What will be happen? So if we decrease the potential difference between cathode and anode, the photoelectric current also decrease slowly. Even at zero voltage, there are still some photoelectrons with sufficient energy, or we call as the energetic photoelectron, will be reached at the anode, and photoelectric current flow at this time we call as I naught. Then we reverse a power supply terminal where the positive terminal of power supply we connect to cathode, and negative terminal of power supply we connect to anode. What will be happen? The anode will become more negatively and will be repel the photoelectron. It will make the photoelectric current drops until its value equals to zero. At this time or this moment we call as stopping potential voltage, or Vs. So stopping potential, or Vs, we can define as the minimum value of negative voltage when there are no photoelectron reaching the anode. According to the conservation of energy, the potential energy due to this retarding voltage now equals to maximum kinetic energy of photoelectron. We can write as U equals to K max where U or potential energy is EVS and K max or half M max squared. E is stand for charge of electron, Vs stand for stopping voltage, M stand for mass of electron, V mass is stand for maximum velocity of electron or photoelectron. Alright class, this is our last slide for photoelectric current. And look at this graph, where this graph is photoelectric currents again, voltage. We have two parts of this graph. We have part before reversing the terminal and after we reversing the terminal. Okay, look at before reversing the terminal, we can find out that when we increase the voltage, the photoelectric current also increase until a saturation photoelectric current. And after we reversing the terminal of power supply, the photoelectric current will be decreased until 0. And at this time, we call as stopping voltage. Okay class, that's all. Thank you. Bye.